Topic 5, acid-base review. Welcome to topic 5. This is a review of acids and bases. I'm going to ask that you guys look at these notes first. They are in your workbook. Because it's review, I'm going to breeze through this topic pretty quickly, and then we'll do the examples at the end. So go ahead, you guys can pause the video and read through your notes, and then I will do the examples with you. So here we have the 5 formulas that you learned in Chem 20. There is one other formula which is going to help fill the gap in between your hydronium ion and your hydroxide ion, and we're going to do that when we look at Kw. So that is coming up in a next lesson here. So I'm just going to show you guys a diagram chart that I like to use with all of these formulas in it. You guys can draw it on a quiz or on a test, and it'll just help you get from one spot to the next. Hi guys, so here's a little chart that I like to do just to show you guys all of the different formulas that we can use for acids and bases. So say I was starting with a pH and I wanted to know my hydronium ion concentration. I can go from pH to hydronium ion concentration using my formula that my hydronium ion concentration equals 10 to the negative pH. If I started with my hydronium ion concentration and I wanted pH, I know that pH equals my negative log of my hydronium ion concentration. Now I know for pH and pOH that pH plus pOH equals 14. So if I had pH and I wanted pOH, I know that pOH is going to be 14 minus pH. If I had pOH and I wanted pH, I know that pH is going to be 14 minus the pOH that I was given. Now that I have pOH, I can go to my hydroxide ion concentration. My hydroxide ion concentration is 10 to the negative pOH. Or if I was given my hydroxide ion concentration and I wanted pOH, I know that pOH is going to be negative log of that hydroxide ion concentration. I could also go from hydroxide ion concentration to hydronium ion concentration in one step, but that lesson is coming later. One more note, please watch your significant digits. Remember, for a pH or a pOH, we're only looking at the numbers after the decimal place. And for our hydronium ion concentrations and our hydroxide ion concentrations, whatever number we have given are the significant digits. So watch your sig digs in your answers, depending on the information that you've been given in your question. All right, hydronium ion, I'm not going to go through this, you guys know this. It is important that we understand that why can the pH of a 1 mole per liter solution of an acid have a pH anywhere from a value of nearly 7 to a value of nearly 0, depending on the specific acid, and that is because we have strong and weak acids. So if we look at a strong acid, that's anything above the hydronium ion on page 8 and 9 in your data book, and they do ionize basically 100%. Sorry, my arrow didn't show up here on this diagram, but this is basically a quantitative reaction. This should be an arrow here where this question mark is. And this tells you that when hydrochloric acid reacts with water, you're almost completely going to get hydronium ions and chloride anions, and you're going to have none of your reactant left over. So because this ends up producing so many hydronium ions, the concentration of our hydrochloric acid to begin with is the same as the concentration of our hydronium ions, or it all becomes hydronium ions, giving it a very low pH. Weak acids, however, again this is an arrow and this should say 1.3% right here. Weak acids, however, do not ionize 100%. Here we have an example of acetic acid reacting with water. Its percent reaction is only 1.3%. So if we had, say, a 1.0 mole per liter solution of acetic acid, the concentration of our hydronium ions is going to be much lower than 1.0%, because this only ionizes 1.3%. And we'll get into what this concentration is going to be in subsequent lessons, but it's going to be less than 1.0 moles per liter, which obviously means then the pH is going to be higher or closer to 7. So even though we start with a concentration of 1 mole per liter, like we had with our HCl, because HCl is a strong acid and it ionizes almost 100%, this one ionizes much less. The concentration of the hydronium ion, which is what we're measuring when we measure pH, is going to be much different and then affect the pH because of that. All right, so strong bases are cations with hydroxide ions, which dissociate completely in water. So they are aqueous strong acids or strong bases. Now, if we think of something like calcium hydroxide, when we look at our periodic table, or sorry, not our periodic table, when we look at our solubility table, we can see that calcium hydroxide is in fact going to be solid. So we actually don't consider calcium hydroxide to be a strong base because it does not dissociate into those hydroxide ions because it is a solid in solution. So we get very little hydroxide ions. Something like sodium hydroxide, though, is a strong base because it is aqueous in solution and it does dissociate 100% into sodium ions and hydroxide ions. So keep that in mind. We don't talk too much about these, but you guys will see them around a little bit. Weak bases do not contain hydroxide ions. However, they still dissociate partially in water to produce hydroxide ions, and that's when we're looking at our modified Arrhenius theory. So we're going to get to our modified Arrhenius theory in our examples. So here we can see that sodium carbonate dissociates into sodium ions and carbonate ions. Those carbonate ions react with water and produce those hydroxide ions and our HCO3 negative. So I'm just gonna go through these examples with you guys. This is your modified Arrhenius theory when we do the examples coming up here. All right, so our revised definition of acids and bases, that collision reaction theory keeps on coming up. So we need to think about this substance's reaction with water and then the nature of the hydrogen ion. So our collision reaction theory tells us that compounds collide and the collisions make observable things happen. Our modified Arrhenius theory is that a solution reacts with water to form hydronium ions. So there is a reaction that is taking place with water, and bases are solutions which dissociate or can also react with water to form that hydroxide ion. So we need to think about these reactions that are taking place for both acids and bases with water. Are they forming hydronium ions or hydroxide ions? All right, so just reviewing modified Arrhenius before we start here. If we've got a polyatomic ion, we're going to dissociate the ionic compound if it's required. So say we had something like NaHCO3, we would dissociate that, right? Na positive, HCO3 negative. We're going to continue the reaction with the polyatomic ion. Check the reaction of chemical with water, and is it most likely to produce a hydronium ion? In fact, if it is, it would be an acid, or is it going to produce a hydroxide ion with water, and then it would be a base. And then the other product should be a recognizable chemical formula, usually some sort of ionic compound. Usually some sort of polyatomic ion. All right, so let's go ahead. We're going to do these examples. Okay, so here we have NaHSO4, which may, when we're first looking at it, not really look like an acid or a base to us, but we have to remember our modified Arrhenius theory. So I've told you guys that blue litmus paper can turn red. This is because HSO4 negative can technically gain or lose hydrogens, but what it actually does is it tends to lose hydrogens to make a hydronium ion. So if that's the case where one thing could possibly gain or lose, you will be given some sort of diagnostic test to help you guys decide whether an acid or a base is what the entity is. Now when we're looking at NaHSO4, the first thing that we're going to do is, because it's in solution, we're going to dissociate it. So NaHSO4 is going to dissociate into its ions, and we're going to have Na positive and HSO4 negative. Now, there is no way that Na positive is going to react with water to produce hydronium ions, and it's actually not going to act as a base either. So we are just going to ignore our cation here, and we're going to work with our HSO4 negative. Now we can react HSO4 with water, and this hydrogen ion can be donated over to our water molecule. So the HSO4 donates a water molecule, or sorry, a hydrogen ion over to H2O liquid. What's going to happen here then is because our HSO4 negative has lost a hydrogen, it becomes SO4 2 negative, right? It's lost a proton, and our water has gained that proton, so it becomes H3O positive. So NaHSO4 does in fact react with water to produce hydronium ions, making it an acid. Okay, our next example was if we took ammonia gas and we bubbled it into water, we would get NH3 aqueous. Now, if NH3 or ammonia is going to react with water, what happens here is now the water molecule donates a hydrogen ion to ammonia, and you guys could probably see here that NH3 becomes NH4 because it's been given a hydrogen proton, that's NH4 positive. And this is something we know, right? We can look on our polyatomic ion chart and see the ammonium ion. Of course, what is left then from the water molecule is the hydroxide anion. So that tells us that ammonia acts as a base in water. Now, just really quickly, if we had ammonia and water, and the opposite happened, the hydrogen went to the water molecule, we would end up with NH2 negative and hydroxide ions. But the thing is, what is NH2 negative? It's not something that we're familiar with, and it actually doesn't exist. So what you're looking for on your product side is something that is quite common to you. And of course, ammonium should be very common to you guys by now. Okay, these next two are just something that you kind of just need to memorize. So a non-metal oxide acts as an acid when it reacts with water. So when you think about a non-metal oxide, it's something that has oxygen in it, but that other thing is a non-metal. So carbon and sulfur, both of these are non-metals. When we see them with oxygen, we call them non-metal oxides. I like to break my non-metal oxide reactions with water into two steps. So my first step, I'm going to take carbon dioxide and I'm going to react it with water. And I call this the mashup step because I'm just going to put everything together. So I end up getting H2CO3. Right? H2CO3. There's my three oxygens. Now my second step, I take my H2CO3 and I react it with water a second time. Oops, sorry. Just one water. And now what happens is I'm going to donate my hydrogen from my H2CO3 to my H2O to make that hydronium ion. Because I know non-metal oxides are acids, so I have to have a hydronium ion as my product. So H3O positive is going to be one of my products. And then because my H2CO3 has lost that hydrogen ion, it now becomes H, right? It's lost the second one, HCO3, and it's lost a positive charge, so its charge now is negative. So non-metal oxides will react with water to produce hydronium ions, meaning they're acids. Now, if you want, you can show this in one step, right? I could make a net reaction out of this. So carbon dioxide gas reacts with 2 molecules of water. Right, my H2CO3 cancels out on either side, and I end up with H3O positive and HCO3 negative. So there it is, just in one step. All right, and then just quickly here we've got our example with SO2, exactly the same as what I did with CO2. SO2 reacting with water, the mashup step produces H2SO3. I take that H2SO3 and I react it with water. The hydrogen is donated from the H2SO3 to the water molecule to become H3O positive and HSO3 negative. This hydronium ion tells me that it is an acid. So just memorize, that's all I can tell you, that non-metal oxides react as acids in water. Okay, last example. Now we're going to look at metal oxides, and metal oxides act as bases. Again, just something that you need to memorize. So a metal oxide here, we can see we've got oxygen with a cation. That cation is a metal. So that's a metal oxide. So very similar. I still do 2 steps. So calcium oxide plus H2O. This one's a little weirder to see, but you still get something that you're used to seeing. So here we have calcium hydroxide, and we have 2 of them. So the oxygen here and these 2 hydrogens make our hydroxide here, and then we do have our calcium, which we end up with, right? So the second step is to react it again. So calcium hydroxide, and if we put that in water, like I said, the reason why this is a weak acid is because this remains mostly solid in water. However, anything that's only slightly soluble is still just that, slightly soluble. So you're going to still get calcium ions and hydroxide ions here. So because we still got those hydroxide ions, when this dissociates, we are going to call this a base. It's a weak base because we only get a few hydroxide ions from it, right? We could calculate a percent concentration, or we could calculate a Kc, and we'll do that later on. But you can see here, a metal oxide is going to react as a base. Here's the mashup step. This is kind of just the confusing part. You're going to make the hydroxide here, and then you're going to dissociate it and get those hydroxide ions. So that's why it's a base. I find it just easier to remember that non-metal oxides are acids and metal oxides are bases, and then just writing my equation accordingly. I'll share the link with these 2 videos. One is about superacids and one is about the most dangerous chemicals in the world. They're both pretty cool, so take a look. Okay guys, that is the end of topic 5. I just thought I'd take the opportunity to show you guys the coolest thing that my husband has probably made in our house. He's made lots of things, but this is like an epic concrete planter that he made. This is one of my favorite things. Okay, hope you guys are well. Miss you lots. Take care. Bye.